This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
This is Robert for Software Engineering Radio. Today I am joined by Martin Thompson. Martin Thompson is one of the leading experts in the field of computer system performance and tuning. He's a frequent speaker at technology conferences, the founder of LMAX, a high-frequency trading firm. He is one of the founders of the open-source Disruptor project, and he maintains the blog Mechanical Sympathy. He's currently the proprietor of Real Logic Limited, a computer systems performance consultancy based in London. Martin, welcome to Software Engineering Radio.
Hi, Robert. How are you doing today?
Very well, thank you. Martin, please tell the listeners a little bit about your background and how you got interested in performance.
Oh, it's kind of interesting. I've done many different things in a career spanning back a few decades, but kind of interestingly, I always seem to get dragged into areas whereby if computer performance improves in an area, new opportunities are opened that just weren't possible before. I think back the very first thing I did in this sort of space was back in about 92, where I was taking feeds from the Toronto Stock Exchange, and at that time we were having to process everything on IBM mainframes. But the feeds at that stage could actually fit onto 2 hard disks if you installed them into a PC, when hard disks at that stage were around about 250 megabytes. So I think today we've got caches that are sort of starting to come up into that sort of space. But yeah, we could get data into that, and we could open up new opportunities where businesses could do things that they just couldn't do before. And my kind of career has gone on through many different things, through sort of modeling of vehicles, dealing with large catalogs, dealing with trading systems, very different domains, but kind of with performance and high throughput being an underlying feature through most of it, and kind of hardcore computer science, which is good fun to do for a living.
The name of your blog is Mechanical Sympathy. What do you mean by that?
Yeah, Mechanical Sympathy is an interesting name. I'm also a big fan of motor racing, and the term comes from a racing driver called Jackie Stewart, who in the 1960s and 70s was an incredibly successful racing driver, and he particularly was incredibly smooth and very good in the wet. And he talked about having mechanical sympathy for the vehicle he was driving. When he showed mechanical sympathy for that vehicle, he could get much more out of it than other drivers. And this is where, particularly in the wet, it showed very well, where you know where the limits are. You push up to the limits, but not beyond the limits, so you get the best out of it. And for him, it was about working in harmony with the vehicle. For me, it's kind of similar with software and hardware. Whenever software shows a mechanical sympathy for how the hardware and platform works, it works in harmony with it and you get the best out of it. Too much software you see today works against the underlying hardware with very limited understanding of it, and as a result, not just performs poorly, can also have robustness issues whereby things are just not used correctly and edge conditions pop up and things start to go wrong. This doesn't mean you need to understand things in minute detail or be an absolute expert. It's about understanding what is important and distilling the essence of what is important when using the underlying hardware, so understanding the basic characteristics. Just like in motor racing, if I need to drive a very fast car, I don't need to know how to rebuild an engine, but I need to know how it works. I need to understand how the basics of a gearbox works, how the basics of suspension works. By understanding that at a fundamental level, I can then get the best out of it. Similar applies to software.
Could you give us an overview of the basics of computer hardware that you think are poorly understood by a lot of software developers?
Yeah, there's lots of great examples of this, and a lot of it is actually naming conventions that we use in this space, which actually leads people the wrong way. The names we choose for things is very, very important, and it programs people's interaction. Like, for example, we talk about random access memory. Yet access to memory is not random at all. There's orders of magnitude difference between whether you access memory sequentially or whether you access it completely random. Because of how the hardware works, it takes a number of bits and does things to make memory much lower latency. So it hides the latency to main memory in how we access stuff. Now, if I go through memory sequentially, it can almost completely hide that, and we can be accessing memory at what effectively looks like less than a nanosecond on a modern PC. If I start accessing it completely random, and this is without even building up queues inside our infrastructure, we're looking at anywhere from sort of 70 to over 100 nanoseconds to access. So the same memory on the same machine, but just with a different access pattern. So what this suggests is, in fact, that memory behaves very much like a serial device, more like tape than it does as a random access device in how we access it. Hard disks have got very similar characteristics, even SSDs have similar characteristics, but most people are not aware of these things, and they just will access the underlying memory subsystem with very little understanding for how it actually works, and as a result get performance issues.
In reading through some of your blog posts, there's a consistent theme of the extent to which program performance is dominated by the relationship between the CPU cores and the layers of CPU caching. Talk a little bit about the importance of that.
Yeah, that's something that very much does jump out when you start monitoring and profiling modern software. We have very small caches organized into a cache hierarchy of ever-increasing sizes, but also ever-increasing latency. So, for example, your CPU doesn't actually work on main memory. It never does. It loads that memory into internal registers, performs operations on those registers, and then stores that memory back out. Again, it doesn't store that memory directly to main memory. It stores it to the cache subsystem. Cache subsystem is the source of truth in our modern computer systems, and they spill back to main memory whenever the cache subsystems have reached the point of exhaustion. So the follow a least recently used type algorithm whereby we end up pulling in data, and data that's used recently will be hot in cache, and that's a useful thing. So that's one of the bets, is memory that is used recently is likely to be there. So it's a temporal type bet. It also pulls memory in chunks. It doesn't pull memory in bits or bytes. It pulls them in cache lines or in pages, depending on which layer of the cache subsystem we're dealing with. So memory that's close together tends to benefit from being pulled in together. And then it also takes a third bet on patterns of access. We have hardware-based prefetchers in our cache subsystem that are looking for patterns of access through our code. And based on those patterns of access, we'll actually prefetch the memory into those caches. The L1 cache is where the processor is working directly with. It's only 3 to 4 cycles to access that. So you're looking at the sort of 1 nanosecond time period to access that. You go out to the L2, which is a larger cache. So you've typically gone out from a 32K cache to a 256K cache on a modern Intel processor, stepping out to your L3, which is anywhere between sort of 2 and 30 megabytes, depending on what model you've bought. And those, as you've stepped out, get bigger, but also higher latency in how we get to them. Now, where this starts to matter is the algorithms we choose. We're taught computer science in school, and we learn about the order of algorithms, but the order of the algorithms does not take into account the underlying hardware. Like a good example being a linked list. If I want to walk a linked list, it should be the same order of algorithm for the linked list versus an array. It doesn't say it's going to be significantly more if I look at the order of the algorithm. It is a different order of the algorithm if I want to randomly access any given element. An array has got order 1 for any random element, and it will be in order n with a linked list. What's much more significant is if I start walking a linked lists are implemented as nodes with pointers off to the elements that are held in that list. Those could be anywhere randomly in memory depending on where that memory's been allocated. And as a result, you've got a random access pattern in memory. Hardware prefetchers can help us. The fact that data that is co-located gets taken together, again, that doesn't help us. And the temporal side doesn't help us unless we happen to have just accessed that data very, very recently. So there can be as much as an order of magnitude difference dealing with a large array versus a large linked list and how we access these things. These patterns also continue through things like maps and trees and all sorts of other structures. And that we have to be aware of what those units of access for the data currency is when we deal with data as we move it in and out of our CPUs to manipulate it.
What I think you're saying is the hardware architecture makes certain bets about how the program's going to access memory, and it would make sense for programmers to program in such a way that their bets will be right most of the time?
Yes, that is correct. So there's so many bets that the hardware makes. There's the 3 bets I talked about, the fact that it's a time-based bet, there's also the spatial bet, and there's a pattern-based bet that's taken care of. There's always more and more silicon and intelligence keeps getting invested in making that better, but it's only so far it can fundamentally go. If you completely randomly access your memory, as a result, you will get the poorest possible performance because the hardware cannot help you out. That in fact goes further. It's not just your data, it's also your instruction stream. So our processors are also taking bets on branches and how we're going to be predicted. Modern processors speculate on which way a branch is going to go because it may not have the data yet. So whilst it's waiting on a cache miss to retrieve data that is going to make a decision on an if branch in your code, it can actually make an assumption that that's true or false and proceed executing more instructions. If it later finds out that that bet was wrong, it has to throw everything away. If it turns out that bet was right, it's already made progress and the bet has paid off, so our code can be faster. And then that comes down to, well, if it's keeping statistics on your branches in your code needs to be predictable. It needs to follow similar sorts of paths. If it's very random, it's going to lose out on that. If it's predictable, it won't. The interesting thing is many branches in code can quite often be replaced by mathematics when you think about the algorithms and how they can be applied, or even just getting back to a cleaner understanding of the domain model. There's a lot about how modern processors and runtimes work, that if you want really good performance, you want to have small, clean, quite linear methods that are very composable. Large methods with lots of branching, lots of looping are incredibly hard to optimize from the CPU level, the OS level, runtime level, right up through our stack. So sort of clean, very predictable code runs incredibly fast. It's also very easy for humans to read and reason about. So they're not at odds with each other. I quite often hear people saying, oh, but if I optimize my code and I design it for high performance, it won't be readable. I find that that is blatantly not true. In fact, it's quite the opposite. Nice sort of clean, elegant methods, well decoupled, high cohesion, nice and simple and composable, in fact, performs incredibly well for high 90% of the use cases that you'll actually apply. There'll be a few edge conditions where you have to do something a little bit specific, but that's much more the exception than the rule.
A moment ago, Martin, you were talking about arrays versus lists. I ran across one of your blog posts in which you suggest that a lot of the standard libraries in common programming languages are not very machine-friendly in their basic data structures. Is that the case?
That's very much the case. So the most popular language in the world, Java, for example, if I want to lay out an array of structures, and a really good example of why I might want to do that is I might want to implement a much better implementation of a hash map. Inside Java, I have to have an array of references. Those array of references then point to nodes that hold the beginning of the chain for each chain for every given bucket inside the hash map. It would be much more efficient if I could lay out a contiguous array of structures that are the start of those buckets. I remove the step of indirection and I have got a nice striding-based pattern for how to get to those first-level structures right through if I need to probe forward. These sort of things are not built into the standard JDK. It's written in a way that is perfectly designed to cache miss almost constantly. If you take an extreme difference, the dictionary implementation in C# is implemented with a very memory-friendly layout, and for data sets I've measured at 2 gigabytes plus, it's at least 10 times faster to use the layout of the dictionary in .NET versus the hash map in Java. And there's lots of other examples. Without even needing massive changes in Java, most of the time we key into different data structures based on primitives. So it may be a long, or it may be an int, or some other very simple key-based system to get into it. If we use open addressing and linear probing style hash maps from there, again, we can get nearly an order of magnitude improvement in performance where we hash directly to a location and we probe forward. We're walking through memory in a nice friendly manner, and it's all laid out in an array for how to access that. There's only one of a number of examples. I could go on with trees, for example. People implement binary trees where we should be implementing n-way trees where we're pulling in blocks that have a number of nodes to a number of children. The same sort of techniques that we used to apply on disks when developing databases, we should be doing the same thing in memory on our data structures. A lot of our data structures that we're using in common languages are not designed with this thinking. It even goes further than that. The guys who developed the collections libraries in Java have comments in the source code that you can go in and read where there's constants in the code for different factors, and the comments next to them say like these factors should be revisited on a regular occurrence and updated created based upon new measurement. Since those were created many, many years ago, to my knowledge, they've never even been updated once.
Wow. I have another library-related question. In one of your talks at QCon San Francisco, you were talking about performance tuning. You were emphasizing the very high cost of multiple rounds of copying, that performance is often dominated by a third-party library like a JDBC or message queuing from a vendor, which is doing multiple unnecessary copies. What do you do when you're building a system and your bottleneck is in a third-party library?
That's an interesting challenge. Ideally, you can get an alternative to that library, but that's not always the case. I think a lot of libraries are designed almost as an afterthought. I think JDBC is a very good example of this. They have been improving over time, but still, like for example, we still don't have non-blocking JDBC libraries that are asynchronous. We should have that, and we don't have that in our current designs. But when I've looked into them in the past, you actually see the way the code's been written. It's always been written by multiple teams, where buffers are handed off from layer to layer to layer to layer, and as a result is very inefficient. Sometimes these patterns have been copied from C, where some of those patterns are much more efficient with a handing off of a pointer. In Java, it's quite often not the case because a lot of the code is not designed to work within subsets of arrays, so you end up copying the array over and over again. You see this quite often because even if you don't have the source code, the nice thing about Java is the bytecode can be decompiled. It can also be profiled, and you can see these issues that do exist. On a number of cases, I've had to decompile libraries and put fixes in and try to submit them back to the vendors, or actually come up with completely alternative client implementations whereby the bottleneck in the library was so significant that building a version of that client library was actually the cost-effective way to get our system to scale and perform.
I'd like to talk a bit about multi-core computing. There's a well-known, I'm not sure if this is a paper or a quote, stating the free lunch is over. What did the guy who said that mean?
I think you're referring to Herb Sutter's famous essay back
Okay.
around about 2007, 2008. What Herb was pointing out at that point is that we reached the point whereby as we're shrinking the manufacturing process and the thermal densities are going up so high that we can't keep increasing clock speed. So for a number of years we have been having this free lunch of every 18 months. Our CPUs are effectively doubling in performance because of the doubling of clock speed as we improve the manufacturing process, but we've hit a wall with that, and it seems incredibly difficult to get CPUs to clock much more than 4 gigahertz without having serious thermal issues because you can't dissipate the heat. So CPUs are getting faster. So there's an interesting point that since then CPUs have not been getting faster at the rates they were getting faster. They are getting faster, but the rate at which they're getting faster has significantly slowed down since that point, and that's because clock speed is staying largely the same. Processors are getting smarter, but more interesting is actually the cache subsystems are getting smarter. The processors themselves quite often are not the limitation in our systems. If you measure most systems, you'll see that your processors are idle most of the time. They're just not being fed data fast enough, and that's where the real action is. The real action is how do we feed data and instructions into our processors fast enough to actually execute them, and that's where the memory subsystems are coming into play. So understanding that we have a hierarchical memory subsystem, we have a memory subsystem now that's even gone non-uniform in how it works. So you'll hear the term NUMA, non-uniform memory architecture. I quite often see this as an issue where people buy a multi-node server and they don't realize that memory is connected to individual nodes within that server. Even at the very simple end, you've got a 2-node server where there's a socket that has got memory connected to it, and you've got another socket in the same machine with memory connected to it, and those 2 sockets are connected by a high-speed interconnect. Well, traversal across that interconnect is 20 nanoseconds each way, so a round trip is an additional 40 nanoseconds. So if I'm accessing memory from one CPU socket that's connected to the other CPU socket, I'm adding 40 nanoseconds to everything. And it doesn't matter whether it's in the cache subsystem or the memory subsystem of the other socket, I've still got that 40 nanoseconds added on as an additional cost. Quite often, you can get a huge speed up in systems just by using some OS level binding to say, okay, if I want to run my program be that a JVM or C program or anything else, if I have sufficient memory and sufficient cores to run all of my threads that need to run on a single one of those sockets with a single memory region, it can in fact be up to 3 times faster than spread across both of them, which the operating system will do by default. And people don't seem to be aware of that. One of the things I find quite shocking is now that you can go to somewhere like Dell's site, and in the past, if you wanted to buy a large memory system or a large core count system, you went through the channel and you dealt with a provider like Sun or IBM or HP, and the person who's managing the channel would have a sensible conversation with you about what software do you need, what hardware do you need, what's the usage you're going to be, making sure you purchase the right thing. What we start seeing now is people can self-service. You can go onto the Dell website and you can click all the boxes that you want and get something delivered. The problem is people just think more is better. So they'll have extra sockets, extra memory, just extra things inside this machine. They may even choose not to have a 2-socket machine. They may have a 4-socket or an 8-socket machine, where some of these pneumo facts start to get magnified even more, so the trips between the nodes can be 1, 2, or 3 jumps even between the nodes in the mesh that's in there, which adds significantly more latency to all accesses to memory, which then really hurts performance. And so as a result of spending more money on hardware, their software actually slows down. And it's through to that lack of mechanical sympathy for the hardware in which they're running.
Would it be fair to say that most systems are not getting N cores of performance out of an N core machine?
I think that is very fair. If you actually measure most systems, you'll find that a lot of the cores are just sitting idle most of the time. And even more so, you start getting interesting effects where maybe 1 or 2 cores are running at 100% and the rest are sitting idle because there's a contention point in the design of the software. And that contention point means that everything else is bottlenecking and going through that. That's where things like Amdahl's law and Little's law kick in, and you're trying to model what's going on in the software. That can be even further than just the software itself. It can be the runtime. For example, if you're running on something like a Java runtime and you're allocating lots of memory and the garbage collector needs to come in, there's times where all of the threads have to be brought to save point to allow the garbage collector to continue. Bringing all of those threads to save point means there's no progress being made on those threads, and you'll find that you've got lots of idle cores. And when you bring all threads to save point, you may get 100 threads to save point incredibly quickly, and one thread may take a long time to come to save point because it's doing something like a memory copy or allocation of a large array or a large clone of an object, and everything has to wait for it to complete. You don't make progress on those other 99. You have to wait for all 100 to reach that point, including the slow running thread to come to save point, and then progress is made on whatever the JVM is going to do, like going to do garbage collection, or it's going to do class unloading or optimization or lock rebiasing. There's lots of things that can be going on inside our JVMs at that point in time. And it's not just Java, it can happen across many other managed runtimes. In fact, other managed runtimes like, say, maybe PHP or other sort of things like Python are actually even less well designed for scaling up to incredibly high core counts because they haven't been thought about in advance to do that, and so we get limitations where with bottlenecks in the code, bottlenecks in the runtime, and as a result, things are serializing on those bottlenecks and nothing else is making progress.
You just brought up the JVM, and I would like to come back to that, but first I'd like you to discuss these 2 core concepts of system throughput, Amdahl's law and Little's law, which you just mentioned.
Yeah, the 2, I think there should be bread and butter understanding for most people who are working on large systems or systems with any performance needs, and even moderate performance needs. Amdahl's law does a very nice job of describing the limitation in which you can scale up any algorithm by adding extra cores to the problem. So, for example, if my algorithm is 95% parallel, but it's got 5% of it that must happen sequentially, you can't throw more than about 20 cores at it and you just fail to get any more speed up. And it's also asymptotically approaching that. So your scale up is fundamentally limited because you end up with as many cores as you throw at it, waiting on that 5%, and then that starts to magnify up with the number of threads that you throw at the problem and available cores. It's kind of fascinating just watching how quickly it comes and gets you. As we've been sort of dealing with 2-core machines and 4-core and even going to 8-core, most of this has been reasonably hidden, but it starts getting big and ugly very quickly as you start approaching 16, 32, 64 cores. So I kind of like to look at it in algorithms, like if you have a serialization point, you can't run from Amdahl A will hunt you down and your algorithm will be fundamentally limited in how much it can scale, even at single-digit percentage points for any part of an algorithm that's required to be serial across all of the different threads. And so much requires being serial. Like people can even just miss it on simple things like having a cache in their software where the cache has got a lock around mutations to that, and there's lots of mutations going on. Everything is now serializing on the cache, so they think they're actually improving performance, but they could be massively hurting performance. That's kind of Amdahl's law and how it describes the serializing component and what potential speed-ups you can get. The one that works nicely hand in hand with it is Little's law, which describes the queuing theory that happens around points of serialization. So as soon as you've got a point of serialization in your code, only one thing can use it as a time. As a result, a queue can form. And with queues forming in your system, you start to see your impact on latency. Because the queue forms, your latency grows. As a result of your queues unbounded, your system can just get ever-increasing latencies, and then it actually gets worse after a while because you start using up all of your memory, especially when you have unbounded queues in your system. And I know queues are everywhere, whether people realize it or not. If you have a lock, a semaphore, anything like that, people think they don't have a queue. Well, guess what happens to everything waiting on getting that locked resource or resource protected by some sort of critical section is then must queue, and those queues are unbounded, and unbounded queues can just grow unchecked. At that point, what happens whenever they don't any longer fit inside the cache subsystem? You're out to main memory, and on a least recently used algorithm, the poor thing that was struggling to keep up with consuming is now hit with cache misses on top of it, and as a result, your system very quickly dies. I'm a great believer in that if you have unbounded queues in your system, you've just got a crash waiting to happen, and it's going to happen wherever you least want it.
One of the themes in your writing and blogging is the extent to which multi-threaded program performance is often dominated by the cost of coordination and switching rather than doing actual work, which is what you want it to do. Why do the best intentioned programs end up so badly when you go to multiple threads?
I think it's because of the change in hardware and how systems have been developed. We've been typically running on uniprocessor systems for a long time. Even a lot of current developers have been working on uniprocessor systems when they've cut their teeth. And now we've gone multi-core. Like, for example, if I was on a uniprocessor system running Java code, the JVM will actually remove all locks from the code because you don't actually need them in the case of a uniprocessor system, because you'll never have another thread hitting that data at the same time. You'll be time sliced until the point where another thread runs. Now we're in a world of true multi-core. We're having to genuinely apply locks and memory barriers and have the mutual exclusion applied. And one of the problems with all of this is signaling to other threads when something's done. Simple example of this is if I want to offer to a queue and take from a queue. So if I go to take from the queue and the queue is empty, and if I've done a blocking take from that queue, I have to go asleep. So I end up calling into the operating system and asking to have my thread suspended at that point. Whenever I go to offer something to the queue, at that point what happens is the thread that goes to offer to the queue has to let the operating system know that there's something now in that queue and to wake up that other thread. That whole housekeeping of having to wake up that other thread and signal via the operating system is incredibly high cost. On a modern operating system, that can be anywhere between about 3 and 15 to 16 microseconds to carry out that operation. That is often way more processing cycles than it actually requires to do the business logic that's sitting around that. So the design of sort of making things multi-threaded and having locks and condition variables to hand off between stages can quite often greatly impact the performance of the software, where you'd be better off just writing it single-threaded. One of the things I try to encourage people to do is actually see if you can get your business logic to run on a single thread. And quite often you can, and it's sufficient to run at that stage. The problem is you can't be making blocking calls. But a lot of people design software that is synchronous and makes blocking calls. As a result, you can't run it on a single thread and you can't scale up. So you need to move to a more event-based pattern and make non-blocking calls. And then you can have effectively single threads of execution running without all the headaches of concurrency and the performance downside that comes with that.
You are one of the contributors to an open source project called Disruptor, which does embody some of these concepts that you're describing. Would you tell us a bit about the thinking behind the disruptor and how it solves some of these problems?
Sure. Some of the things I've done in the past is working on high-performance gaming sites and financial exchanges. And one of the challenges in those environments is incredibly high throughput, like literally into the tens and hundreds of thousands of operations per second that need to occur. But combined with that is a need for very low and predictable latency. So what you need to do is get that throughput to happen with the low latency and also with as low a jitter as possible. And in doing that, we looked at many different designs, and the disruptor came out of just a number of natural design pressures pushing the design in a certain direction. It wasn't a case of, let's sit down and dream up the disruptor. It was a case of, look at the requirements, look at the natural design pressures that we were having imposed upon us, and how do we evolve a design to meet those design pressures. And so it evolves out of that. And so whenever we were building exchanges, a number of things that you try to do is to make it incredibly resilient. So to make something resilient, you need to be saving data to disk, you need to be replicating it to other nodes, you also need to be on-marshalling that data that's coming in and off the wire, and you need to be doing the business logic and repeating that all on the way out. Well, a lot of those things can run completely independently as long as they're synchronized, and not synchronized in a lock sense, but synchronized in a timing sense at the right point in time. So for example, I can be writing entries to disk whilst I'm replicating those entries to another node or a number of other nodes, whilst I'm also on-marshalling that data, getting it ready to be invoked by the business logic. As I'm processing stuff, I want to do that as fast as possible with the minimum overhead. So the design of the disruptor is again based on mechanical sympathy. So how can I run all of those threads in parallel? How can I have a really low-cost coordination that keeps everything in step and let each of the other threads know when different points have been reached? And that's all done using concepts known as lock-free algorithms and how it works. It's also designed to take garbage collection pressure off the JVM, because if you want a very low jitter environment, you don't want to be allocating a lot of garbage, because a lot of garbage then means garbage collection cycles. And with many of the current VMs that are out there, they have issues with doing concurrent collection, and instead they fall back to stop the world pauses that pause your application as well as everything else that's happening, and then as a result you can't respond and have low latency. So the design of the disruptor is to pre-allocate all of the initial data you have and then just reuse it over and over again in large ring buffers to pump data through the system. And as a result, you can build very high throughput, very low latency systems with the proviso that you always have enough cores to run threads that want to run. The failure case I see with people using the disruptor is they try to run way more threads than they have cores available. And in that case, it's not the sweet spot for the use of the disruptor. So if you've got a 16-core system but you want to run 100 threads, it's not designed to run well in that scenario. If you've got a 16-core system and you've got 10 threads that need to run concurrently, it can do incredibly well and give you very good throughput.
Martin, why a ring buffer?
A ring buffer is interesting because of that mechanical sympathy thing. So with a ring buffer, you go around it, reusing it over and over again. I mentioned earlier that our hardware takes bets on things like recently used data and having predictable access. As I go around a ring buffer, I've got predictable access to memory. So the hardware prefetchers can be pulling that memory in and making it available to me. So it's there as I go to use it. Also, as I hand off from producer to consumer, it's hot in the caches and can be moved between them very effectively. It's a technique that's used within most hardware. Part of the interesting side of studying hardware is you learn a lot of things about data structures that work incredibly well that also work very well in software. So if you look at how most network cards, most drivers of most descriptions are designed, they all use ring buffers internally, yet modern software very often does not use ring buffers.
Another concept you mentioned a moment ago that is a common theme in your writing is the lock-free algorithms. Tell us what lock-free is and why does it matter?
Yes, so as I mentioned before, whenever I'm sort of entering a critical section between two threads to mutate some data, or I want to signal from one thread to another that a change has occurred, that is typically done with a lock for the critical section and a condition variable to signal the change that's going on. Now, the condition variable may show up as a wait notify pair in Java. It may show up as a signal and an await statement in Java. If you're using Java util concurrent, if you're using POSIX, it will be mutexes and condition variables that are under the hood. But they're all basically mapping down to the fundamental structure of something that provides a critical section and something that does the signaling. Whenever this is to happen, if your lock is ever contended and when you need a signal via the condition variable, you have to get the kernel involved. So you end up calling into the operating system kernel to get that happen. That's a very high overhead process. I like to think of it, it's like asking the government to get involved or asking the lawyers to come and help you make a decision. It works, it's safe, it's effective, but it's incredibly high cost. Those operations end up costing millions of cycles in how they actually end up executing. The other side of it is with lock-free algorithms is you decide not to get a third party involved. What you do is you agree a set of coordination steps between threads that are coordinating, and they signal change by making memory visible in a predefined order. And for that, you need to take control over the ordering in which changes happen at particular points of an algorithm so that it can be seen. So if we think of you and I want to interact on a task, I can work on part of the task, you can work on part of the task, and we can agree points at which we will share and interact. We just need to agree what the protocol for that is and make those points of the protocol visible to each other. Lock-free algorithms allow us to do that. So within user space in a program, different threads can communicate without getting the kernel involved by applying a number of techniques. Those techniques are typically, how do I make memory visible in a certain order? Because our compilers and our processors will try to do lots of things out of order to get more performance, as long as the illusion of any given thread looks like it happens in the order of your program. It doesn't need to happen in the order of your program. A good example would be if I have a loop, and inside that loop I do some modifications to some data, some calculations, but I also need to increment my loop counter. Does it matter if I increment the loop counter at the beginning of the loop, in the middle of the loop, or at the end of the loop? As long as it's done by the time I then go around and check again, that's all that matters. And our compilers and our CPUs will reorder to get us performance to make that happen. These sorts of things start to matter between threads, because if the visibility changes in order now, I've got a problem coordinating with another thread, so I need to put hints into my code, not even hints, directives to say certain things must happen in a certain order when they're visible to another thread. And so that's one part of it, is getting that whole memory ordering and visibility correct. I think that's the most important point. The next most important point after that is certain operations need to happen atomically, and they can be a multi-step operation. So for example, I may want to try something and I may fail, so I may want to increment a counter. So me signaling that my work is done, I may do that by incrementing a counter. If multiple threads can increment that counter, you can get a lost update. Like one thread reads it with value 10, another one reads it with value 10. They both do an increment and try to set the value to 11. Both succeed, and as a result, one of those increments is lost. What you need to do to overcome that is use techniques that are known as CAS, compare and set, or compare and swap techniques, whereby I will conditionally update that counter if it's in a state that I know. So that would be a case of, like, I read the variable, it's 10, I do an increment and I go to write it to be 11, but I'll write it to be 11 conditional on it being 10. If it's not 10, I'll fail, and I can go around and try again. And so lock-free algorithms are about those two major things, is making sure all the things happen in the correct order and certain things happen atomically so a coordination can happen. And with those two basic things, you can build up most algorithms to have coordination. If it's multi-step, you just build it as a state machine. We do one step, then another step, then another step, just like we would do in real life.
Several times you've brought up the issue of Java garbage collection. Do you feel that the evolution of most programming languages from malloc and free to garbage collection has been an improvement or a mixed blessing?
It's an interesting one. So if you have very specific use cases, you can usually take control of memory allocation and reclamation yourself much more efficiently than any general purpose means of memory management. So a good example of this is actually using a ring buffer to exchange memory from a producer to a consumer. But a lot of things don't have that. In fact, it can actually be quite tricky. What if you've got multiple producers, multiple consumers, or you hand off things to other threads? So in a multi-threaded environment, managing memory is incredibly tricky. People say, okay, well, I'll use reference counting, but reference counting then needs to use those CAS-based techniques that I've just been talking about, which are actually very expensive. And so handing memory around in a multi-threaded environment using reference counting is probably one of the slowest means by which you can do that. Garbage collectors take away a lot of that problem by collecting concurrently and basically using tracing-based garbage collectors. So they find things that are reachable and removing that. And it takes away a whole class of bugs. I've done a lot of programming in low-level languages and higher-level languages that have garbage collection. And when you've got garbage collection, it definitely takes away a class of bugs that you just don't have to worry about anymore. It's just access to memory on the whole, so having things like bounds checking and range checking and different things that are useful gets rid of a class of bugs that you generally don't catch in languages like C. But it usually has a cost. What's fascinating for me about this subject is theoretically a garbage collector can be the most efficient general purpose way of allocating and reclaiming memory. A truly concurrent generational garbage collector, when you're able to allocate sufficient memory to the problem, can beat pretty much any other general purpose allocation and reclamation model. The problem is most of our garbage collectors are written with quite simplistic views around how we collect in particular, and that they expect the world to be stopped to do certain phases of the collection. And by stopping to do certain phases of the collection, there's parts of that cycle ends up having a serial component which has Amdahl's law involved. So it stops us scaling up, and it also causes nasty pauses in our algorithms as they execute. There are collectors out there that are truly concurrent with our code and give us incredible efficiency of allocation and reclamation. One good example is the C4 collector from Azul, but it's the only one that I know that's commercially available that can give us those sorts of very high throughput rates and collection rates and be very easy to use without pauses.
Given Amdahl's law, is there an inherent limit on the number of cores that a JVM can use effectively if the entire rest of the program did not have any bottlenecks?
It seems to depend on how much allocation you've got and what other things are going on. So bringing threads to save point is one of the biggest issues within our modern JVM. So there's a number of cases that cause that to be a problem. So bringing threads to save point is that if I want to do anything that involves a stop the world pause, the first thing I must do before I do that work is bring all threads to save point, at which point I've now stopped the world. So I could be doing a garbage collection cycle, I could be doing class unloading, I could be doing de-optimization, I could be doing lock rebiasing. There's a number of things that can be happening in the JVM, but I need to bring all of those threads to save point first. That is a serial problem. So I think one of the most important things within the JVM is we've got to have things either not happen under save point so that they don't need to stop the world pause. They are truly concurrent. I think that's one major step. The other major step that we need to have is even when we do need to use save points, we need to go around checking all parts inside the JVM where you've got a long path in getting a thread to save point, because even if you've got one thing that takes a long time to get the save point, it's going to hold everything else back. And as a result, Amdahl's law is kicking in at that point. So there needs to be significant time spent on time to save point within the JVM. To add to this point, a really good way to highlight it is a lot of people measure the garbage collection time in their applications. One flag that should be turned on is application stop time. And you'll often find that application stop time is significantly greater than the time to do the garbage collection. That is because you needed to bring all of those threads to save point, and it's usually what the component of the time is. I quite often find in measuring systems that bringing threads to save point is greater than the actual work being done, like say, be that a phase of garbage collection.
Wow. So to what extent have you seen that the performance of Java server programs can be substantially improved by tuning the various garbage collection switches and parameters?
You can see it happening quite a lot. There's kind of two classes of problems I quite often see here. One is someone has actually gone about tuning it and they've done more harm than good, and they would have been better off leaving the system with defaults. And maybe they've put in tuning parameters that were based upon a behavior that was seen in an old version of a JVM, and they've kept those tuning parameters and they've gone through a number of upgrades, and they're now hitting points where some of those configuration options they put in are harmful rather than helpful. The other side is quite often a case that people have just misconfigured for the basics of what's going on, so that they haven't profiled their application to see how much heap do I need, what size of new generation do I need, what size of survivor generations do I need, what size of old generation do I need, and just by sizing things correctly based upon live data sets and what you're seeing in promotion rates to avoid that can have massive impacts on just improving how your application runs. But it's just taking the time to do that. The biggest challenge with most of this, I find, is most people don't have representative tests to actually run in a performance environment. They're just trying to react to problems they're seeing in live systems. They don't have very good monitoring on their live systems, if any, and they've got no way of recreating what's been happening on their live systems. As a result, they just can't tune. And they're just flying blind and making guesses. And I think that's one of the biggest problems I see with systems not being designed to perform or do well, is people just don't have a performance environment and suitable tests.
What are some of the key things that systems should be monitoring with a view toward using garbage collection smarter?
Turn on garbage collection logging. I think it's a key point. I've written a blog article on garbage collection distilled. The goal for that blog article was to give people an overview of what are the basic type of collectors that come within the JVM and what are the basic tuning parameters that are in there. And also at the end of that, I've given some sort of minimal flags that should be turned on so you get logging of the right information. Once that information is there, you can then input it into certain tools. And it's very low overhead on a production system. You can turn on garbage collection logging. Generally, most people won't even notice that it's turned on. And from there, you can then take the results of those logs, put them into a tool and analyze them and see what's happening to your application.
You spoke earlier about the inability in the Java language to define an array of records rather than an array of references. In some of your talks, you mentioned the concept of off-heap structures to get around this. Could you tell us a bit more about that?
Yes, so to get predictable memory layout means that we can then get predictable performance from our memory subsystems. And so the languages need to give us the ability to do this. I don't think it's a feature that everyday developers need to use, but I think it's particularly very important for library designers. So we should be able to design maps, trees, all sorts of other collections that internally are well designed for memory usage and giving us good memory performance. Unfortunately, Java as a language and the bytecode that's underneath that doesn't have the expressiveness to let us lay out memory as we need to. And I think there's three major cases where we need to have control over memory layout. One is to be able to lay out an array of structures or an array of objects so that I can stride through those and avoid the indirection. So by dead reckoning, I can go to any given structure without a dereference step to get to there. Because each dereference step with the cache miss can be 100 nanoseconds added to your cost. But it should be just dead reckoning, go to that check, and then I should be able to walk forward from a point with predictable stride. And as a result, avoid all of that. I should be able to do similar things in having a block of a node that's an n-wet tree, so I can do B star trees of any description and do those efficiently. Those should be the things that underlie our basic collections. And by having those features, we can then build much more efficient collections. So that's point one, is being able to lay out memory as an array of structures. Second point on this that we need is we need to sometimes inline or cluster one object into another. And a good example of this is, say I have a queue structure and I've got a head and a tail. Well, I don't want to dereference off to an object that contains the head or the tail descriptor. I want to have that inline and reach it by dead reckoning as well. So again, get rid of that dereferencing. So I should be able to collapse small objects into large objects. The good examples of this is like the things like atomic long, atomic end. Small objects that are wrappers around a primitive type that should be able to collapse back into an object and lay that out very efficiently. Third thing that I would like to be able to do is be able to extend something dynamically. So this is very similar to the concept of a C structure that has a variable length array at the end of that structure. Where that's very useful is for things like, say, the string object. The string object has got some fields in there to say things like the hash code, the length of the field, or an offset within that field. And then you've got the array of bytes that come after that, or the array of characters that represent the string itself. Why do we need to have an object that represents a string with a dereference off to another object that represents the array? The array should just continue on contiguously at the end of that object to give us that memory locality and to deal with that again by dead reckoning without the indirection offset. JVM can start playing some tricks for things like string because it knows what string is, but I should be able to design almost any structure like that and make sure I get a nice efficient layout in how it works. And I should be able to design libraries knowing that some of these features exist. They don't need to be language changes. They can be done with simple intrinsics and some patterns that are agreed in advance that the JVM looks out for and then applies the intrinsics based upon those patterns in code, just like they do for all of the other intrinsics that are in the code. With these features, we can get orders of magnitude improvement in certain collections and certain access patterns.
How would you change computer science education for undergraduates?
I would focus a lot more on things like the scientific method being part of the education, learning to work from reason, measurement, and science. I think that should be fundamental, just as you would get in a science degree in any other subject, having it instilled. I think sort of learning about how to learn, how to reason, how to keep up with the ever-moving subject material, and being aware of things. Like, it's very easy for humans to fall into the populist approach and follow fashion. It would be nice to look more at the fact that things do move and how do we keep up, but how do we keep up and know that approaches are solid and sound. Because there's one thing we can be certain of in our subject matter, is that it's going to be changing at a phenomenal rate. And if you were to learn a lot of specifics at university, they're going to be out of date incredibly quickly. So you need to be learning an approach that's sustainable over the long term, and what are the things that matter. So people talk about agile. I think it's important to talk about things like feedback cycles. What's core in agile is that you design things so that your feedback cycles are as short as possible. With short feedback cycles, you make better decisions. In fact, it's okay to get stuff wrong. If your feedback cycles are very tight and you've got very little waste, you can then make rapid progress and even deal with failure on the way. But we get all these talks about stand-ups and all the ceremony around agile, and we don't talk about the fundamental principles that underlie it, and that's what's really matters. That's what matters, I believe, and I think we need to do that with computing, learning how things work, learning how things work from the ground up. I think in the modern world, most people now graduate with a computer science degree and they have never programmed in a language that has any direct memory access at all. And it's nice to be able to abstract above that, but if you don't know the fundamentals to how it works, you're just going to make bad decisions because you're just assuming it's magic, and we're into the realms of witchcraft rather than science.
Martin, if listeners would like to learn more about your ideas and your work, how should they do that?
My blog is one point where people can start and look at Mechanical Sympathy. Or you can also go and join the Mechanical Sympathy discussion group on Google, where there's some great chats that happen there, where we have people discussing a lot of these subjects and digging into more detail and kind of getting back to basics and how things fundamentally work.
Are there any conference presentations that are available on the web that you'd like people to have a look at?
There's various things I've done, and hopefully I'll do more in the future. So if you Google for my name and presentations that are on InfoQ or YAL and some of the others that are out there, hopefully it gives a starting point. I had it described to me that my blogs are usually the start of a very good wiki walk. They get people exposed to new concepts and they can go off and then understand more from that point. So I like to introduce people to something. It's not that they're going to learn everything they ever need to learn from that one point, but it will hopefully start a thread that they'll follow on and learn more from.
Great. Well, Martin Thompson, thank you so much for speaking to Software Engineering Radio.
Oh, thank you for having me. It's been a pleasure.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or /dot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.